Hey everyone, can you hear me okay? Fantastic. All right. Well, we have about 1 minute before we can get started, but we will have a few people jump on here. It looks like we have several coming in. So we'll get started in just a sec. All right, it's officially 11 o'clock on Central Standard Time, so we're going to go ahead and get started. Hello and welcome to part 3 of our 2021 CTR series. My name is Casey Craig. Many of you know me as Stella's mom and the Acute Syndrome Foundation moderator and social emotional program director. I am so happy to spend this next hour with all of you today. Karen Varner, Lily's mom, I'm already gonna get emotional, posted in our family Facebook group today, encouraging us to share things we are grateful for. Instantly, this group came to mind. Unfortunately, many of our kids are struggling right now. Seizures, intubations, hospitalizations, big scary med changes, and currently Stella refuses to puke, so I'm terrified she has a bowel obstruction. Whatever your challenge is right now, please know you have a big group of people around the world in your corner and sending love from near and afar to you and your child. Today, I am grateful for our family support group and the medical professionals that have focused their life's work to improve the quality of life for our precious children, which is a perfect segue to our topic of discussion today, the science of SCN8A and potential future treatments 101. Dr. Eric Wingert is here with us again today, and he's going to give a presentation that will be an expansion of his annual SCN8A 101 talk to include the information on science behind potential treatments for SCN8A. If you're unfamiliar with Eric's talk, he's hands down amazing. As a former member of Manoj Patel's lab and now working with Dr. Ethan Goldberg's lab at CHOP, not only is he super knowledgeable, but he's an excellent teacher and is able to explain the science portion of SCN8A in a way it's easy to understand. And we're so happy to have him here with us today. Before we get started, we do have a few housekeeping items. Group interaction through questions and/or comments will take place in the chat box only. The chat box is to your right and allows you to type questions and/or responses for Hillary or Eric. If you're experiencing any technical issues, you may type a request for help in the chat box. Our fabulous technical guru, Megan Varner, will help you tackle any technical issues you might have today. I also want to extend a huge thank you to our platinum level CTR sponsors, Neurocrine and Praxis, for their continued support for our community. And don't forget, part 4 of our 6-part series will take place next Wednesday at 12 p.m. Eastern Standard Time, where we will chat about how families can help beyond clinical trials. I hope to see you then. Now I'd like to introduce our very own Hillary Savoy. She is the director and founder of the Acute Syndrome Foundation, and much like Eric, has dedicated so much of her life to our SCN8A community. I'm forever grateful for her endless fight for our kids and her friendship. Without further ado, Mama to Esme and her dog Prim, Miss Hillary Savoy.
Thank you, Casey. And hi, Eric. Welcome. Just have a few words before we get started today. Like Casey said, I want to take a moment to recognize that our community is going through a really, really difficult patch. And I tend to have the response to these moments to just put our heads down and work as hard as we possibly can. But sometimes that's hard to do. And I just want to acknowledge that a lot of us are struggling right now. A lot of our children are in the hospital right now. And part of the idea behind this series and the work that we do at the foundation and the work that we do with partners like Eric and our biopharma partners is with an eye toward the future, right? When we understand the science better, when we have a treatment that works, when we get through the clinical trial and we can go to the pharmacy and ask for this amazing drug that was made just for us. But when your kid is sick and in the hospital, those moments feel really far away. So I just want to acknowledge our support community is always here. We're here for our families. We're here to answer your questions. We've been working one-on-one with several people who are hospitalized right now and trying to make sure that they get everything that they need. And I want all of you to remember that we are here for that as well, and will remain here for that. We're here for today, and we're here for tomorrow. So with that, I'd like to take a moment to introduce one of our favorite people. Eric, just hands down, has been just an amazing addition to the SCN8A community. He has done SCN8A 101s for this community for, I think it's literally ever. Is that right? Just forever, Eric? Okay, yeah, so I think it's forever. He has come and talked to us, answered all of our questions, from the really basic to the really complex, and helped us understand the science of SCN8A. And this is really important for us to understand every bit that we can, so that we can engage as much as we can. We can understand what's happening in our children's bodies and why it's happening to the extent that that's possible, and why further research is important. And today, when I asked Eric to come on to speak today, I asked him also to talk a little bit about how we apply that knowledge to looking at the potential for future treatments. So with that, Eric, you want to turn your mic on, and we can, I feel like I'm hanging with an old friend.
Yeah, which is good. Can everyone hear me?
Oh,
Can you hear me?
I'm having a little trouble hearing you. You sound a bit like a robot. Does anyone else have the same?
I sound robotic. I am a scientist.
Oh, he's fine on your end. But to me, he sounds like a robot. Okay,
that's unfortunate.
So
this will be a long talk.
Eric, you're going to entertain the crowd for a minute. I'm going to pop out and pop back in and see if that fixes the problem.
Okay. Well, I'm happy to entertain the crowd. I
promise you don't have to run the whole session on your own.
Great. Well, I do want to say, for those of you who can hear me in the non-robotic way, and I'm really happy to be here. And yeah, I'm thankful that we can gather virtually like this. I think that's the pandemic's been terrible in many ways, but one good way is, I think, organizing us for meetings like this. And of course, I'd love to be with you all in person and hope to do so again soon. But this is good for today, and I'm really eager to present kind of an adapted version of my 101 talk. So I guess we'll wait just a second to see if Hillary hops back in and if everything is good on her end. But then once I get the go ahead, I will go ahead and share my screen, and then we'll dive in. I suppose I can even begin with just an introduction of myself. So just for those of you who have met me, it's great to be together again. If this is your first time joining in, or we haven't had a chance to meet, my name is Eric, like it was said. So I finished my PhD just this past year. I was previously at the University of Virginia with Minaj Patel. Many of you know him as well, and his lab focuses on SCN8A epilepsy. Is this any better, Hillary?
It's perfect now. Yeah.
Okay, great. So I was just introducing myself, and then is it okay for me to share screen and dive in?
Absolutely. You should. Maybe I should just leave. You can do the whole thing, right?
I'm good to go. Just let me know if there are any problems,
okay.
And then
awesome. Thank you.
It should be good. Thank you. Anyway, yeah. So I just finished my PhD with Minaj Patel, and then I just started in July in the lab of Ethan Goldberg, where I hope to continue working on SCN8A as well as other epileptic encephalopathies. It's a really great lab. Ethan is an excellent mentor and an excellent physician as well as a researcher. So I'm really eager. I'm not going anywhere. I guess I will be here till I'm 80 years old, still giving this 101. But no, I really enjoy this, and so thanks for having me. I'm gonna go ahead and share my screen and try to make sure everything is good. Let's do this. So do you see my SCN8A 101 presentation? Can someone chime in? And
yes, we can see it.
Okay, great. Okay, I just want to always make sure. So I only have one screen I'm chiming in. So I always like to make sure that I'm not somehow sharing my email while I'm presenting a PowerPoint. So Yeah, so we have titled this SCN8A 101 in the past. I thought about maybe calling it SCN8A 102 since we're continuing on in our kind of basic trying to describe some of just the foundational aspects of neurophysiology. But today we're going to extend it a little bit and talk about epilepsy treatments and ones that are on the horizon, and talk just a bit about, as a researcher perspective, how we think about epilepsy treatments and how we are going about the task of trying to pursue better treatments for patients with SCN8A epilepsy. So I want to disclose just a few things. So here are the disclosures. I don't have any current conflicts of interest relevant for today, but my lab in the past has worked with some of the companies relevant to today's discussion. I just want to make sure that's everyone knows that. Okay, so are we ready for a virtual format? I like this slide because my cat occasionally makes appearances on these Zoom calls. So if she chooses to chime in, don't be worried. I haven't duct taped her to the wall. We will have today just about 30 minutes of lepture material, or just I'll try to present some basics as we think about SCN8A epilepsy and as we think about epilepsy treatments. After that, we'll have plenty of time for questions. I'll do my best to answer. As we get more into the clinical realm, I'll always be forefront that I'm not a physician. I'm not a medical doctor. I can answer some of the basic science questions, but certain questions that you have for me, I think I will have to sidestep a little bit. And I hope that's not frustrating, but I do encourage you to follow up with folks in the medical field who you are in touch with for certain clinical questions. But I'll do my best to answer whatever questions are given today. And then if you have more, you can always follow up with me. So here's my personal email. I invite you to reach out if you do have questions, or if you just want to connect. As a researcher in this field, I'm really passionate about building bridges between the research community and the family community, and so don't hesitate to do that. Okay, so let's dive in. This talk is going to look a lot similar to what you've seen from me previously, but it will be a little bit different. So whether this is your third or fourth time seeing 101 or your first, I hope that you can get something out of it. And yeah, and so with that, let's dive in. Let's talk about SCN8A epilepsy, and I always like to start off the talk with really big picture kind of stuff. The question, what are brains for? I like thinking about this because it orients the discussion and in a way that I think can be helpful. And so brains, fundamentally, I think you can think of it as it is an organism that regulates the nervous system within the body, ultimately to help us interact with our environment and to live. So brains are great at taking in the senses from around us. So whether it's the sense of vision or sense of hearing, or even the sense of touch on the body, those senses allow us to take in information in our surroundings. The brain processes that, it gathers all of that information, and then it helps us orchestrate an output, whether that's movement or speech or some sort of behavior. And ultimately, it's all about staying in good balance with the world around us. So a brain is what tells you if you're outside in the winter that it's cold and you should go inside, in order that we would actually be able to live and remain in good balance. And so brains are this highly complex input-output device, taking in information from the world around us, processing, and helping us orchestrate an output. And within the brain, if you zoom in even further and look at individual cells, there are specialized cells of the nervous system and in the brain, and they're called neurons. And they are the cells that actually communicate with one another to perform the functions that a brain does. Well, neurons are specialized in the sense that they are excitable. And that just is another way of saying that they are electrically active. They actually can signal to one another using changes in voltage, which is electrical potential energy. But just think of it as blips of electrical activity in neurons are actually the way that they can communicate with one another. And neurons are really beautiful. You can see an old classic drawing of a neuron, or just examples of neurons that are filled with a dye when you perform patch clamp experiments like I do. They're really, really beautiful, and throughout the whole brain, they are very diverse, making the brain difficult to understand in its full complexity. I'd argue we don't even understand how a single neuron fully functions. And so a large aim of neuroscience is to try to understand how nerve cells function and communicate with one another to perform brain function. And why would neurons use electricity as their signaling? Well, one way I like to think about it is that it's just extremely fast and extremely reliable. Changes in voltage can happen and can be passed on over long distances without the signal getting disrupted. Reminds me a lot of our power grid, the ways that we actually use electrical energy flowing through cables to communicate with one another all around the world and to power our devices. So it shouldn't be too surprising that the brain actually co-opts this form of communication. It's highly reliable, extremely fast. So let's go a little deeper in thinking about how exactly neurons communicate using changes in voltage. Well, the actual change in voltage that neurons use to communicate is called an action potential. It's this spike in membrane voltage, which is used to signal between neurons. And so I like to think of this action potentials as the language of neurons. And just to show an example from some recordings that I've collected in my research, you can see how a neuron does this. If you take a neuron and you actually record its function, and you just listen in and you don't give any stimulus, or if you just give a little bit of light stimulus to the neuron, you can see there are no action potentials. But if you drive that neuron with a more moderate stimulus, you can get a few action potentials, here about 9. And if you zoom in, you can see this spike waveform in membrane voltage. And if you give an even stronger stimulus, you can get even more action potentials, higher frequency. So essentially, the neuron is transforming whatever it's taking in as a stimulus, and it's orchestrating an output that corresponds to the number of action potentials. So if it wants to send a strong message, it has very high frequency action potential. And if we zoom in on each of these action potentials, they consist really basically in 3 parts. A resting phase, which is just the very beginning where the membrane potential is just stable at rest. The rising phase, where the action potential begins and the membrane potential quickly rises, the membrane voltage rises. And then this falling phase, where after it peaks, it starts to come back down to rest again. And it's the progression through these phases that a neuron undergoes when it's firing successive action potentials. And so since this is, these are the language of neurons, this cycling through these phases is extremely important to consider when thinking about how neurons function. So again, just to recap, we talked about the brain, we zoomed in on neurons, the specialized cells that communicate within the brain, and they communicate by speaking the language of action potentials. Where do voltage-gated sodium channels come in? Well, voltage-gated sodium channels are special in that they are responsible for generating these action potentials. I'm going to show you in what sense I mean that. So let me orient you. First, I have a cartoon neuron over here on the right, and I have this little red box showing that I'm zooming in right on the membrane, which is just the edge of this neuron. We have the inside of the cell and the outside of the cell. And I've also have these circles, which represent ions. The yellow represent sodium ions, while the green, potassium. Well, what's an ion? just briefly, an ion is any charged particle. So it just has a positive charge here. And that means that whenever it moves, it can actually create changes in electrical voltage by becoming an electrical current as it moves. And so in cellular systems in the brain, on the inside of a cell, there's very low sodium. So you see there are no yellow circles in here. Where on the outside, there's a lot of sodium. What this concentration gradient means is that the sodium wants to flow into the cell, just down its concentration gradient, but it can't do so because it can't actually just cross this membrane. It can only pass through by going through a channel that's specifically designed to conduct sodium. In this case, a voltage-gated sodium channel can allow sodium to pass through. However, voltage-gated sodium channels are special in that they have two gates. Both gates have to be open in order for sodium to flow. And so we actually, from these two gates, have three distinct channel conformations. First, you'd have a closed channel in which the activation gate on the voltage-gated sodium channel is actually shut. And that means sodium can't flow. But in the process of activation, this gate can swing open, and for a moment in time, both gates are open and sodium can flow into the cell. And because it's a positive charge flowing in, it can actually activate that cell electrically. The open channel is extremely unstable, and so within just a few milliseconds, it closes itself by shutting this inactivation gate. So the inactivated channel also can't conduct sodium. So we have closed, open, and inactivated, and channels progress through this cycle to conduct sodium. Well, why does this matter? Well, let's put these two pieces together. I talked to you just a second ago that there are three phases of an action potential: the resting, rising, and falling phase. And there are three channel states of the voltage-gated sodium channel. Well, it turns out that the voltage-gated sodium channel actually drives this change in membrane voltage. So initially, when you're at rest, your voltage-gated sodium channels are closed, and sodium is not flowing into the cell. But in the process of activation, when the channel opens, that's when the sodium rushes in and the membrane potential rises. And then quickly after that, channels inactivate by shutting the inactivation gate, and that initiates the falling phase, the falling phase of the action potential to complete the cycle. And then eventually, these inactivated channels will once again become closed channels, and the process will happen over and over again as the neuron fires action potentials. Well, why does this matter? Well, this matters in the context of SCN8A because any small tweak in the process by which channels progress through these states will have implications for the action potential. Either it'll change the shape of this action potential waveform, which will change the message that the neuron sends, or maybe it'll have too many action potentials or too few. And these small changes, seemingly small at the level of the channel, can have very large consequences when multiplied by the thousands of action potentials that neurons send every hour, multiplied by the 80 billion neurons that are in the brain. So you can see how this process of how channels progress through these states is very important from the perspective of a researcher trying to understand how voltage-gated sodium channels relate to neuron function. Well, what about SCN8A? So I just gave you a brief few notes on neuroscience and neurophysiology, but we're here to talk about SCN8A epilepsy, and I haven't even mentioned really SCN8A yet. Well, let's talk about it. SCN8A is the name for a gene that codes for the NAV1.6 voltage-gated sodium channel. So it's one of the voltage-gated sodium channels, like what I was just showing you about. Well, what does this mean, gene and channel? Well, it's a bit complicated, but the simple way to think about it is that SCN8A is the part of the DNA that contains the instructions that the cell uses to build the NAV1.6 channel to actually conduct sodium. And when we talk about mutations or variants in the SCN8A gene, we're talking about a change in that genetic sequence that actually just changes the way that the channel gets made. So for an example, in the research community, we use the N1768D mouse model of SCN8A epilepsy. And this N1768D is a shorthand way of saying that in the 1768th position of the peptide sequence making this channel, what is typically an N has been switched to a D. So one single change in this whole way of building the channel is able to change the way that the channel functions. I've also added two terms here that I've added this since the last time we've had this talk, because I always get this question, well, what about loss of function mutation or gain of function mutation? These are simple terms, even though the reality is a little bit complex, but these terms are helpful in simplifying that roughly we have two ways that the channel can be altered. The mutation can either make less sodium pass through. That might happen if the gates stay shut more, or they're more prominent to be in the closed position, or you have extra inactivation. That would be a loss of function. Less sodium passes into the cell. Or you, on the converse, you'd have gain of function, in which the gates either open or fail to shut properly, and that would result in more sodium passing through. So those two terms, as you've heard, and many of you already know this, but that's just a simple way that the research community thinks about the ways that variants can change how the channel functions. Okay. So we've gone through brains, neurons, action potentials, and a little bit about SCN8A, but what is epilepsy? It feels almost strange to be explaining epilepsy to this community because, as I've said before, and I'll emphasize again, you all are the experts of SCN8A epilepsy. I research it, yes, and it is the object of my investigation, but you see the personal close-up view of what epilepsy is and what it does, and how SCN8A is even more than just a seizure disorder. But I do, as we were thinking about for the remainder of the talk, considering anti-seizure medications, I want to just start off with a really simple way that the research community thinks about what epilepsy is and what seizures are, since that will orient the way that we undergo translational research, or research aimed at helping to generate novel treatment strategies. So what's epilepsy? Well, epilepsy is a disorder where patients have unprovoked seizures. And seizures, from the brain perspective, we can think about it as resulting from activity that is both hyper-excitable and hypersynchronous. These terms just mean too much activity, too many action potentials in a simplified view, and hypersynchronous as all these action potentials happening in a synchronous way, or all happening together in time. So with both thinking about what epilepsy is and what seizures are, I think that in general, much of epilepsy research can be divided into three categories. And the major aims of epilepsy research, one is just much of what we do is looking at individual neurons and seeing how do they become abnormally excitable, and precisely what ways do changes in ion channels, like voltage-gated sodium channels, in what ways do they make neurons change their excitability? The second one would be trying to understand how networks or groups of neurons functioning together become hypersynchronous. How does the brain help prevent against hypersynchrony, and how is that altered in epilepsy. And then a third aim, which I think is relevant for today, is just, how are we able to reestablish balance in the brain and treat epilepsy? And it's that last one that we're going to talk about today, and with a view toward future treatments. And so, for the remaining bit of the talk, I want to go through some of the logic underlying anti-seizure medications, or what used to be called anticonvulsants, drugs that are able to help prevent seizures. Well, as a starting point, I always like to describe, when I'm explaining this either to my students or to others, that it really is oriented towards restoring balance of excitability. You can't just completely block excitability in the brain. That would be very bad, because we need the brain to orchestrate these functions of keeping our body well and responding to whatever is in our environment and orchestrating an output. We need excitability in the brain. So it's not the case that we can just stop action potentials. And of course, many of you have seen side effects of medications that seem to go beyond the balance and actually impair functioning of brain. Even though they block seizures, maybe they don't reach balance. And so this is the goal. It's a very challenging goal. The idea is to inhibit the excess of activity, or the hyperexcitability, but without fully blocking excitability in the brain. And one way that the research community and those interested in developing new treatments, the way that we go about that is to try to make these pharmacological agents or drugs selective. So selectivity is the key to trying to reach balance rather than just stopping excitability. Well, how can you be selective? Well, we can create inhibitors or drugs that block channels, specific ion channels where it only affects one but not others. Maybe the drug only works on ion channel states. When it's in a particular state, the drug is able to bind to the protein and work. And the last one might be for neuronal states, only when particular neurons are behaving in particular ways. I know some of that is abstract right now. I'm going to try to illustrate it with in the next few slides, but that selectivity really underlies a lot of what the research community is trying to do. We know how to block voltage-gated sodium channels completely. Any of you who have been to the dentist have experienced Novocaine, which really does a good job of blocking voltage-gated sodium channels. But it's unacceptable for an anti-seizure medication because we're trying to seek balance rather than just blockade of channels. And before I dive into talking about these particular approaches, I want to mention that I'm only going to discuss a few today for time reasons. I'm only going to discuss ones that seek to directly target and modify voltage-gated sodium channels. So there are many treatments for anti-seizure. There are many anti-seizure medications beyond what I'm discussing. If we wanted to talk about all of them, it would take a whole semester of SCN8A 101 courses. But I do hope that today's kind of overview of a few of these and the logic behind them will be helpful in understanding the goals of how the research community is trying to develop novel anti-seizure medications. Okay, so yeah, I said there are many other approaches, and there are many on the horizon that I won't have, or I won't talk about in the main talk. We can maybe touch on in the questions, but ones like etc. So I'm gonna go over 3 approaches of ways that voltage-gated sodium channels are modulated in a way to try to be anti-seizure. And I'm not going to mention, I don't have it in the talk to mention the exact companies or compounds that these represent in the sake of trying to not sound like I'm endorsing one or the other. It's very important to me that I'm just presenting the science rather than saying that one of these is better or worse than another. So with the first one, approach number one, as I'm calling it, which is perhaps one of the oldest or more classical ways that sodium channels can be modulated to prevent epilepsy or prevent seizures, is to inhibit sodium channels in a usage-dependent manner. And so the background for this view in the logical reasoning is that voltage-gated sodium channels cycle through the closed, open, and inactivated state during action potential. So that's kind of like what I just showed you earlier in the talk. Well, the first premise then is that overactive neurons are the primary cause of seizures. They're the ones being hyperexcitable. And second premise then is voltage-gated sodium channels in these overactive neurons are cycling more than normally active neurons. So that's just another way of saying that neurons that fire a lot of action potentials, by definition, have to be cycling through these channel states more than neurons that fire few action potentials. Well, if this is the case, then for classical sodium channel modulators, they actually bind and help stabilize an inactivated channel. So as neurons have their channels enter this inactivated state, if it's stabilized by the drug, this drug will have a greater inhibitory effect on neurons that are cycling more, because their channels occupy this state more than neurons that are not part of the problem. So in other words, the idea is that in this view, if you inhibit voltage-gated sodium channels in a way that is usage-dependent, you're preferentially reducing the activity of overactive neurons, meanwhile trying to have a limited effect on neurons that are firing at typical levels. And this is a way of trying to, again, silence or reduce the excitability in a way that allows us to achieve balance. So this kind of approach for many of the sodium channel modulators that are currently in use, this is roughly the same mechanism of action. They stabilize the inactivated state of the channel and ultimately block sodium channels more in neurons that are excessively active. So that's approach one. The selectivity is in by inhibiting sodium channels in a usage-dependent manner. Let's move to the second approach. And this approach is one that is on the horizon and is showing, is very well logically based, which is to selectively inhibit just NAV 1.6. And the background for this approach in the logical reasoning is that there are voltage-gated sodium channels other than NAV 1.6 in the brain. Turns out neurons have any combination of NAV 1.1, 1.2, and 1.3, in addition to 1.6. So here in my cartoon, I've added a few more voltage-gated sodium channels. And for this logical reasoning, the two premises are, one, that abnormal NAV 1.6 function causes abnormal sodium currents. That's a way of saying it allows an abnormal amount of sodium to flow through. You can see extra sodium flows through the NAV 1.6 channel. And that secondly, these abnormal sodium currents are the cause of the seizure. If that view is correct, then the conclusion of that logical line of thought would be to inhibit 1.6 as a way of reducing the abnormal sodium flow into the cell and hopefully prevent the excessive activity generated from that sodium current. So in other words, these other channels will be able to pick up the slack and allow neurons to have normal function, whereas the NAV 1.6 that's generating the abnormal excitability, the abnormal action potential firing, will be selectively inhibited. So this approach is really extremely well based, and the difficulty is in designing a compound that can block NAV 1.6 but not the other channels. And so great strides have been made in this area, and it's a very exciting pathway for the research community. And then the third approach, it's similar and yet slightly different. And it has a slightly more nuanced perspective related to the channels. And the additional detail that it considers is that one of the most prominent ways that NAV 1.6 becomes dysfunctional in response to pathogenic variants when you have mutations is that occasionally you see the channels do not progress from open to inactivated, but instead just remain open or persist in the open state. This staying in the open state generates a persistent sodium current, or a lot of sodium can flow through. And it seems to be the case that this persistent sodium current is particularly responsible for leading to seizures. So the premise one here is abnormal NAV 1.6 actually generates these persistent sodium currents. You can see here it's stuck in the open state, and that these persistent sodium currents are the primary cause of seizures. In that line of reasoning, the response would be to actually inhibit the persistent sodium current selectively, only stop and block the channel whenever it occupies this open state for a prolonged period of time, but allow it to do its normal cycling. And so if the channel modulator here, a drug that just blocks the persistent sodium current, it actually hopefully would allow for normal cycling of channels. So when the channels, even 1.6 channels, when they behave normally, they're minimally affected by the drug. It's only when they begin to behave very abnormally that they are blocked. And so that selectivity for the persistent sodium current is slightly unique. One way that's not shown on the graphic, but just to emphasize a step further, is that this drug would also block the persistent sodium current in the other voltage-gated sodium channels. So it's not selective for 1.6, but it is only selective for this type of current that seems to be highly leads to seizures, leads to very excessive neuronal activity and ultimately seizures. And so that is the third approach, and in the logic underlying ways that we can target voltage-gated sodium channels for modulation in a way to hopefully restore balance. And so now I'll just close by summarizing before we move into our questions. It looks like I've gone a little longer, so thanks for bearing with me. Just to summarize, so we started with thinking about the brain. As I call it the master organ of the nervous system. It's what is responsible for taking in senses from the environment, processing that information, and then orchestrating all of the ways that we respond to interact with the world through behavior, through speaking, through movement. The brain is exceptional at doing this, but it requires precise balance. We then talked about neurons as these specialized cells which accomplish these tasks. They communicate with each other using action potentials, these spikes in membrane voltage. The spike in membrane voltage happens because of voltage-gated sodium channels, which progress through these 3 channel states, which in that cycling, we could actually modulate the way that the channel behaves in a manner in which we try to restore balance. And there are numerous ways to do this, and to emphasize that we do this in a way that is selective, either through channel states, neuronal states, or for a specific type of voltage-gated sodium channel. And all of these approaches are founded in the way that we understand how voltage-gated sodium channels relate to action potentials, and we're hopeful that with these approaches, or even a combination or something similar that we haven't yet imagined, that we can hope to restore better function of voltage-gated sodium channels, and ultimately better neuronal function and brain function to allow patients to live more full and seizure-free lives. And with that, it's important to me to acknowledge my team, now my current team in the Goldberg Laboratory at Children's Hospital of Philadelphia. It's been wonderful to get started there and continue on in my work. And again, a major thanks to Manoj, my previous mentor, who introduced me to this field and to this community. Yes, he's just been a huge part of my story, and very thankful to his training. And I always, it's such a priority to me to mention how grateful I am to the Cute Syndrome Foundation, to this community. I normally do it at the beginning of the talk, but today I'll do it at the end and emphasize again how just privileged I am to be able to speak to you, to have your attention, and to have your time. I'm very grateful that this is a session that many of you find helpful. And I just am honored and humbled again that you allow me to present. And I just am thankful again for this time. And I hope that we can have a great question and answer time as we think about some of the science together. And yeah, and so with that, thank you all, and I'll take any questions you have. And I look forward to many of the questions.
Thank you, Eric. We are so grateful to you, and I never ever get tired of hearing you do this. And to have you step it up to discussing the potential of future treatments and treatment approaches, I think is just so helpful for, I think, always for our families. We've got these little bits of knowledge that we're developing, and they're not, and I shouldn't say they're bits, they're big bits, but we're building bridges between them. And so seeing those action potential graphs over and over and over, a lot of us have done that, but then to look at that and understand how something might selectively interfere is so helpful. And so I want to ask one question, clarifying question of you, and then I know we have some questions already. We are lucky enough to have some really amazing parents in our community who are in increasing numbers scientists. Yeah. So you're going to get some.
This is getting harder with each year.
High science questions coming.
I'm just kidding.
So.
This is
good.
Great.
We don't want you to get bored, you know. So the first thing, the clarifying question I want to ask is, all of the sort of potential treatment approaches that you discussed are focused on gain of function.
Yeah,
and
that's
not
right.
Loss of function. And okay, and yeah, and I just want to be sure the families know that, because obviously there's a increasing knowledge about those phenotypes, and maybe a little bit more murkiness than would make it easy on everyone. And to that end, I think we can start with the first question, which is, how do we know if we have a gain of function?
That's a good question. And I just want to, I will in future years modify this talk, because that's actually such an important point. I think for many in my sphere, we've been slightly slow to recognize that loss of function, SCN8A, is also a very present something to consider. I think that even in the heuristic that I give you, that I say seizures are caused by hyper excitability, that's a simplification. And I think with good reason. We have to kind of simplify in order to create a paradigm to guide our questions. But I think it's ever more increasing in how important it is to mention that the loss of function is obviously real and is something that we need to understand better. So how do you know if you have a gain of function or loss of function? I think there's not a great answer to that right now. The way that we do it in the laboratory is actually taking the exact sequenced variant, expressing the voltage-gated sodium channel in a cell culture system, so in cells that we can grow in a dish, and then actually going in and looking at the sodium channels. How do they behave? Do they stay open too long, or do they close more quickly? It turns out that almost all of these variants are actually complex. They never, I would say they don't always fit neatly in gain of function or loss. Those concepts I think are helpful, but as you all know, with the diversity of the ways that SCN8A epilepsy expresses, these constructs are exactly that, constructs. I hope I'm not getting too off topic, but to me, if I'm honest with you, and I speak only for myself here, because I think others like those terms, I almost choose not to use them often, because I think it would be better to just say, this is exactly what this channel is doing, and let's take it and think carefully about it, rather than saying this circle all does this and this circle all does this. With that being said, most of the research considers and thinks about SCN8A gain of function when we are designing treatments that block sodium channels. For loss of function, we would actually we'd predict that a blocker wouldn't be helpful. We'd predict that it would make it worse. The analogy would be with Dravet syndrome. For those of you who may be familiar, we know that sodium channels don't work well in those patients, and so there's a different line of treatment focusing on other channels. And I think for loss of function SCN8A, those treatments would probably be explored as well.
Yeah. I think this is really important, that distinction that it's a system, right? We're dealing with a system, and you change one thing in the system and other output happens, and it's not as easy as, a door opening and a door closing. It's opening and closing into a system that affects everything else. So no easy answers, which is an answer that I think this community is super familiar with.
But we're working. I think I always like to follow up and say that yes, there are no easy answers, but that doesn't mean, without sounding overconfident, doesn't mean that there aren't people who are thinking about this in a really complex way. I have amazing discussions with others in this field who, even though I presented a simple schematic, it doesn't mean that's where our understanding stops. We're really pushing to try to understand the intricacies of this channel, and we're getting closer.
Amazing. Tyler asks, have you looked up other current market ASDs and their selectivity between sodium channels in vitro? My assumption is that most are non-selective, but ESL has in vitro selectivity in 1.2, 1.6 versus 1.1 and 1.3.
I think this is definitely a scientist.
Yes.
Welcome, Tyler. I can't remember if we've met, but I seem to remember some great questions from you in the past. The issue of selectivity, I'm not fully aware if the currently market available sodium channel blockers like carbamazepine, oxcarbazepine, phenytoin. I'm not sure of the selectivity among the sodium channel isoforms. I know that this is a complex issue, including the fact that even in parallel fields, like in the pain field, even things that we thought would be selective in whenever we test them in a dish seem to behave differently in neurons and in mouse models. I'm not sure if that gets exactly at your question, but the selectivity of blockers for ion channels is of immense interest, but I would again say it's not fully understood. Obviously, Neurocrine, Xenon, whatever the proper name is right now, I mean, that's what they're working on with the NAV 1.6 selective blocker, or ones that preferentially hit certain sodium channels and not others. That is heavily under investigation, but my understanding is that the older traditional ones that are still widely used, like phenytoin, again, oxcarbazepine, my understanding is that they are not selective for sodium channel isoforms.
And I'm going to guess that some of that research probably was done as market research internally at some of these companies. It would make good sense, right, that they would be looking to see if there was anything on the market that was accidentally selective or more selective.
Yeah.
But it's a great question, Tyler, and we can try to follow up on that as well.
Yeah.
And then same question, sounds like activity on persistent sodium current. And I think the answer to that is that there are market drugs that are more selective for persistent current. Is that correct?
I think so. We may need to follow up to make sure I understand the question perfectly, but I can say that I know there's some papers about phenytoin being slightly more selective for the persistent than transient. A lot of it also has to do with the precise dosing. So, if you dose it at this particular level, you'll hit persistent more. It's incompletely understood. Also, that you'll see if you do some search, even with recent literature, that compounds that are traditionally not anti-seizure medications can hit the persistent with selectivity, namely riluzole, which was recently there's a publication about riluzole from Jack Parent's lab recently. So there are other drugs that seem to have some persistent selectivity. You mentioned cenobamate. I need to look back. You're pushing my particular knowledge, but
I think Tyler and Eric need to have a drink.
that sounds excellent. But thanks for these questions, though, Tyler. I think they get to the heart of what we're getting at, and I think Tyler has one more question that I'll take now, which I think hits this issue. So I presented a very simple view of sodium channels as functioning independently. The 1.6 functions here and the 1.2 is over here. There is some evidence from a colleague of mine in the Goldberg lab now that sodium channels might actually function in groups of 2 dimers. They may link with each other and function together. So there's a report he has in 2017. That finding may have really, really important implications for this kind of isoform selective, like the logic of isoform targeting certain channels and not others. That may affect the pharmacology. That may affect how these drugs work. If, say, you have a 1.6 and a 1.2 who dimer together and are functioning as one unit, maybe the drug works differently there than on just 1.6 together. And when we investigate these systems and introduce multiple channels at one time. So anyway, that question may have gone a little bit. If you feel like I lost you on that, stay with me. Tyler, I hope that answers your question a little bit. I know Jerome, the guy who published the dimer work, is really pushing on this. So I hope that he can, that you'll see something from him soon. And the Goldberg lab, I would say, is really leading the way on this particular issue. So it's a good question. I can't say much right now, but I know we're working on it.
We have a question from Gregory, if we can get a copy of the slides so that he can translate them to French.
Yeah, sure. That's amazing.
Yes, our European colleagues are really just crushing it over there and making sure that their families are getting access to
good
all of this good information. So yeah, Gregory, touch base with me. Eric, I assume you're willing to share the slides in general.
Yeah, of course. And in fact, I haven't done so already, but and Hillary, you can follow up with others, but like if putting together a video, I know we have this recording, but if a video is helpful, I'm happy to try to do that. And one of the things, I'll put in a small note here, since I have everyone, like I'm actively looking for ways to, if the 101s are a good way for me to be in touch, but if there are other materials that the families think would be really helpful, I would love to align what I'm working on to help what the families want. So that just basically is an invitation to let me know what would be most helpful. I've thought about like a glossary or like a dictionary or terms, or like a little a brief, like writing something up when papers come out, like lay summaries. Anyway, I have a couple ideas, and I really want family input. I don't want to charge forward without getting a sense of what folks want. So that's thanks for letting me just throw that out there and be in touch with what you think is helpful.
Well, we can share this video and the slides and make an ask of the families what would be most useful.
Perfect.
And
Okay.
get back to you. We like to give you work, Eric.
I find this energizing. When things start to fail in the lab, this is a helpful reorienting. So that's all right. More questions.
Yeah. So from Gail, and I want to be mindful of time. We're coming up on 1 o'clock. So maybe we can do 1 or 2 more questions, and then we can bug Eric with more after the fact. But
perfect.
Gail asked, just could you explain the difference between an ASO, which we did not discuss today, versus a small molecule inhibitor?
Yeah, and for that, I am going to share screen really quickly again, because I made a slide on ASOs. Can everyone see my slides still?
Yes.
Okay, so I anticipated this question because I think this is super important. ASOs essentially use the same logic of approach number 2. Let's hide this. And in that, if we could selectively inhibit 1.6, it would be helpful in normalizing neuronal activity. But NAV 1.6 can be inhibited in a couple of different ways. And one way is actually to prevent the cell from making the channel in the first place. And so the ASO actually enters in at the level in between the gene and the channel and blocks the generation of the channel. So antisense oligonucleotides bind to the RNA, which is just, you can think of it as the instructions, an instruction copy of the DNA that's sent to the production machinery to make the channel. It binds those instructions and then degrades them. So it is a sense, it's like blocking NAV 1.6, except it just prevents the 1.6 channel from even being made in the first place. And so it really enters into that same logic and yeah. All right, so I got to stop sharing. Hopefully that was helpful.
We're a ways away from that being a potential treatment.
Yes.
Still. So the small molecules, everyone will come first.
Yes.
ASOs are complicated and are sort of new technology, very promising new technology, but new technology nonetheless. So
yeah.
I think with that, we should probably, I think I got a question from everyone who asked a question, at least one. So I think we should probably wrap it up and let Eric get back to the lab and I know we're more fun, but
yes, so, indeed. Well, thanks again so much.
Yes, and thank you so much for joining us. We like I said, I never get tired of hearing this talk, and I'm especially excited to see it evolve over time. And our families always show up to hear you because you make this feel like something we can all grasp, and that means a lot. So thank you again. And we're also just so grateful for how generous you are with your time. And congratulations again. I didn't, when we were dealing with robot voice, I didn't get to say congratulations on your completing your doctorate. Some of us were there watching you do your public defense, and we're all really proud and pleased to have been a part of that that step in your career.
Thank you. Thank you.
Yeah, and thanks again to the TCSF team, Casey, Megan, Shelley, keeping everything up and running. Everybody, don't forget, same time, same place next week. And we're going to be speaking with several people from a consulting company who are going to help us understand the ways that our community can help move things forward beyond and in addition to any ongoing clinical trials. I'm super excited about this session, and I'm really looking forward to it. I will probably be giving it from Boston Boston, or maybe rushing home to give it from here again, because I'll be going to the Child Neurology Society meeting in Boston and doing some meetings there. So please bear with me if I am frazzled next week, unlike every other week when I have it totally together. So, all right, guys, we will see you again soon. Eric, I'll see you in Chicago, I'm sure. And
yes, I'll be there.
okay.
All right. Thanks,
All right.
everyone.
Goodbye, everybody.
All
Thank you.
Bye-bye.